sharing my screen. Oh, what? Host disabled attendee sharing. That's not good.
Sorry about that.
Okay, there we go. Awesome. Thank you. Are we recording?
Yes, sir.
Okay, awesome. All right, hey. Good morning, everybody. Welcome to the Intro to Quantum Computing workshop. My name is Paul Scott. I'm a senior here at Penn State University Park studying computer science and minoring in mathematics. So this workshop, the idea here is we're going to go over some of the more basic concepts of quantum computing, which is it's a huge emerging field right now in both sort of computer science and physics as well, since obviously we're dealing with the quantum realm. So I'd first like to start off by talking about the difference really between quantum computing and classical computing. Since they are, of course, related, they still perform, they both perform computation, but how they perform these computations is quite drastically different. So first off, both use the same basic unit of memory, which is the bit. So I'm sure we're all pretty familiar with what a bit is. It's either a 0 or a 1. It can represent two states. However, how these computers implement this bit is quite different, as I've mentioned. So the classical approach to representing a bit is using transistors, is using the flow of electrons, the flow of electricity using transistors to represent this either off or on state, 0 or 1. And so we map the 0 to be no flow of electricity and the 1 to be the flow of electricity. And then quantum computing, on the other hand, does something a little bit different. And we represent this 0 and 1 state using quantum particles. So quantum particles operate quite awkwardly and differently than we would expect normal particles to react. So as a classical bit can represent two states, a 0 or a 1, it can't represent anything else. Like that's how we've defined it, that either it represents the definite 0 state or the definite 1 state. However, a quantum computer uses something called a quantum bit, which we tend to shorten using the word qubit. That's much more commonly what it's called. And in a sense, this can be in both the 0 and the 1 state simultaneously. And I'll explain what that means in a little bit, to be sort of in both of these states simultaneously, because it seems a little bit of an odd idea. And we won't know the definite state of this bit, of this qubit, until we actually perform a measurement on it. So when we perform a measurement, it will go to one of the definite states of 0 or 1, but before that, it will sort of be in what's called a superposition of those two states. So I first want to talk about the advantages of quantum computing. So really, why are we researching quantum computing right now? Why is it an emerging field? Well, it's because for certain problems, quantum computing can drastically improve runtime. So for example, if we're dealing with searching an unordered list of items, classical search takes about order n time. And that basically means it has to search through, if you have a list of n elements, it will probably, on average, it searches through about half of them, so n over 2, which simplifies to order n time. But quantum search, using something we'll go over in a little bit called Grover's algorithm, will take about root n time. So that's an incredible speed up. And also quantum computers can solve there are these certain problems that quantum computers can solve much, much, much faster than classical computers, like problems that classical computers would take years and years to solve, like to the point that it's impractical to do it on a classical computer. And then finally, and not limited to, though, that quantum computers can also allow for quantum simulations, which can be really important for modeling things such as chemical reactions and modeling the quantum world. And this, of course, could have huge scientific applications and medical usages as well. Now, obviously, to every advantage, there's a disadvantage, and there are a few disadvantages to quantum computing. For general use cases, quantum computers are actually worse than classical computers. So a quantum computer is probably not going to replace your computer. It's not good at doing sort of the really basic things. And it's because quantum computers are a bit finicky and we're still sort of in the process of researching them. So they are not as reliable as classical computers are for doing very basic tasks. But as I've mentioned, they're really more for very complicated, very work-intensive problems rather than just kind of running like Chrome or something like that. Another issue is that quantum computers will eventually become a security nightmare. The reason being is because there's this algorithm called Shor's algorithm, which allows you to break what is known as RSA encryption. And RSA encryption is what's used for a lot of encryption right now. And quantum computers will just completely destroy that form of encryption. So we are trying to prepare to make sure that there are encryptions that even a quantum computer has trouble solving. And then finally, the one issue, and I'll get into this in a little bit, is that quantum computers rely on probability. And once again, I'll get into what that means, but it means that ultimately, sometimes when we're trying to calculate something and we're looking for an answer, it may not always give us the answer we want. And once again, I'll explain that a little bit further in detail. So I mentioned earlier what this idea of a qubit. So what really is a qubit? How is it implemented and what does it do? So a qubit is a quantum particle that is in what's known as a superposition of the two states 0 and 1. And so this idea in quantum physics is that, this idea is we can't know the state of this particle while we're not observing it. And so we consider it to be in a superposition of all the two possible states until we actually perform a measurement of it. Then it has to go to one of the states, either 0 or 1. There's actually quite a few ways to implement a qubit. There hasn't been sort of one way that's been decided to be the best way to implement it. And this includes electron spin up versus spin down, energy levels of an atom, and also photon polarization. So it's similar to you can implement, there's many ways you can implement a bit in classical computing, although we reuse the transistor because we've gotten really good at that. We still haven't really reached that point in quantum computing. We're still sort of deciding what's the best way to do it. So as I mentioned, a qubit will only collapse to one of these definite states, 0 or 1, when we measure it. But until then, it's said to be sort of in a superposition of both 0 and 1. So then this qubit is very interesting. So when I mentioned that quantum computing is probabilistic, the reason is because when we measure a qubit, it has some sort of probability, which I'll call P0 in this case, for being measured in the 0 state. And it has another probability, P1, of being measured in the 1 state. And so how we represent a superposition of a qubit, how we represent a qubit, is we use these two probabilities. So how do we represent a qubit, at least in the mathematical sense? So a single qubit can be represented using what are known as two probability amplitudes. And I'll explain what those are in a second. So the first one is called alpha 0. You can use any letter. I just decided to use the Greek symbol alpha. And this is the probability amplitude for the 0 state. And so what you do with the probability amplitude is if you take the magnitude of it and then you square it, it will give you the probability that we measured the 0 state. And the reason, though, why we don't just use the probability of 0 is because this allows for our alpha 0 to be a much more versatile number. Since a probability can really only be either 0 to 1, has to be sort of a positive, from 0 to 1 real number. By using probability amplitudes, it sort of allows us to go into the complex range. So they can be, probability amplitudes can be complex, they can be real, they can be positive, they can be negative. But once we take the magnitude and we square it, it has to be a positive real number, basically. And the same exact thing goes for the second state as well, the one state. We also represent it using a probability amplitude. This time, though, we'll call it alpha 1. Same deal. When we take the magnitude and we square it, we get the probability we measure in the one state. And as an important rule, add the magnitude square sums of both of these probability amplitudes, and the result is 1. And that makes sense. That's just probabilities. That's the same as taking the probability of 0 plus the probability of 1. And since those are the only two probabilities, the only two possible states, it has to add up to 1. So to kind of then form an actual notation, a qubit can be represented using the following equation. And you can see we have these sort of weird, this vertical line and this sort of arrow looking bracket. And you can see here, though, we have our alpha 0, so that's our probability amplitude for the 0 state. And this, so this symbol here is just that represents the 0 state, and this one represents the 1 state, as mentioned here. And this is called bracket notation. So I don't really know why they chose this name. It looks like bracket, but it's not. I'm not exactly sure. So aside from using this equation to represent a qubit, it can also be represented using a vector. And so, for example, the vector, and there are two probability amplitudes again, alpha 0, alpha 1. These correspond to a qubit with probability alpha 0 squared of being measured in the 0 state and alpha 1 squared. So just like in the previous slide, except we're now using vectors. But it turns out that the bracket notation that we learned from the previous slide sort of hides the vectorness, if you will, of the qubit. So the 0 state can be represented by this vector 1, 0, and the 1 state can be represented by the vector 0, 1. So therefore, if we take our previous equation and we just, instead of using these bracket notation, we just plug in the vectors up here, you can see that once these just become scalars, and so when we add these up, we get the vector state of the qubit. Now, sort of a nice property is since all the vectors must have a magnitude of 1, all qubit states that, and just for simplicity's sake, we're just going to kind of stick to real valued amplitudes since complex range sort of adds another dimension. But assuming it's using real values, we can show this vector representation on the unit circle, because basically you use the first probability amplitude as the x value, the second one for the y value, and because when you take the square sum of them, their magnitude's 1. So you can represent them on the unit circle. So for example, so we can see here, this vector here represents a qubit in a sort of an equal state of equal probability of being measured in the 0 state and the 1 state. And you can see here they're both positive probability amplitudes. So you can see they're both 1 over root 2, 1 over root 2. If you square both of these values, you get 1/2, 1/2. And then over here, just another example. You can see here you can also have negative probability amplitudes, and this one is for the 0 state having a 3/4 probability of being measured, and the 1 state having a 1/4 probability of being measured. And just a quick note, because we can represent them on the unit circle, assuming real valued probability amplitudes, we can also just use the angle at which they make with the x-axis. So you can replace this with cosine theta and sine theta, like theta being the angle. Okay, so we have our qubits, this basic understanding of a qubit, but what do we actually do with them? I mean, because in classical computing, we can modify bits because we have something called logic gates. And so, for example, we have AND gates, OR gates, XOR, NOT gates, etc. And these are gates that we use. We take bits as input and we output bits based on the inputs. And quantum computers have the same idea. They have something called quantum logic gates. And so, for example, these will be the ones we'll be going over: the Pauli-X Gate, Pauli-Z Gate, Hadamard, and C0 Gate. And I'll explain what they do in a little bit. But so quantum logic gates operate slightly differently than what a classical gate does. So quantum logic gates, actually what they'll do is they modify the probability amplitudes of the state. So they'll change the probabilities of either the 0 state being measured or the 1 state being measured. And each quantum gate is represented by a unitary matrix. And basically what that means is that a simplification of what that means is that the most quantum gates kind of undo themselves. They're their own inverse, so they'll undo themselves. Okay, so the first gate we're going to talk about is the Pauli-X gate. This is most similar to the NOT gate in classical computing. So in classical computing, the NOT gate takes it will take a 0, turn it to a 1, takes a 1, turns it to a 0. It just complements the bit. And the Pauli-X gate does something very similar. If we give it the definite 0 state, it will output the definite 1 state. And if we give it the definite 1 state, it'll output the definite 0 state. But obviously, the issue with quantum computing is we might not just feed it the definite state. We may feed it a superposition of these two states. So given that we do have some sort of superposition here with A being the probability amplitude of 0 and B being the probability amplitude of 1, all it does is it just flips the probability amplitude. So you can see the B went to the 0 state and A went to the 1 state. And you can see this makes sense for these as well, because the definite 0 state, you can just imagine that as having a 1 probability amplitude, and it just moves the 1 to the 1 state and vice versa. This is the symbol for it. It's not very imaginative. It's just a box with an X in it. But then you'll notice right here, we have the matrix representation of it. And so this is when the vector notation of the qubit comes in handy, because we represent these quantum gates using matrices. And this is a 2x2 matrix because our input matrix will only be, our input vector will only be 2 elements, and we want the output to be the same size. So we can see here, it looks sort of like a flipping of the identity matrix. And so you're probably wondering sort of how do we, at least in a mathematical sense, how do we apply these gates to some quantum state? So if we are given a qubit in the quantum state alpha 0, 0 state plus alpha 1, 1 state, how do we apply this gate? And so you can see here, this is the X gate from before. What we do is we take the vector notation of the qubit and we just do matrix multiplication, matrix vector multiplication. And you can see here what ends up happening is when we multiply the matrix and the vector together, the states flip, the probability amplitudes flip position. So the 1 went up here and the 0 went down there. So this is just kind of one of the simpler gates in quantum computing. I think this is relatively easy to understand what it's doing. So let's talk about another one. It's called the Pauli-Z Gate. And before you ask, there is something called a Pauli-Y Gate, X, Y, and Z, but the Y gate takes things into the complex plane. So I'm trying to kind of avoid it for simplicity's sake. So the Pauli-Z gate, what it performs is it negates the 1 state's probability amplitude. So that's all it does. So if we're given some superposition like this, you can see that the output just simply negates the probability amplitude for the 1 state. And you can see if it's negative, it turns it positive. So once again, a really simple gate. And you can see here the matrix that represents it looks a lot like the identity matrix, except the second entry in the diagonal is negated. And so we can see, and if you think about it, if we're applying the matrix, we have like alpha 0 here, or let's use A and B in this case. If you have A here and B here, it would be A times 1 plus B times 0. So the first entry doesn't get modified. Nothing changes. It's untouched. But for the second one, the B entry would just be negated here. So just a really simple action. And this one, though, then the question is like, why would you want to only make the one value negative? Why do you want to flip its sign? Like, what's sort of the purpose of that? And I'll get into sort of a better explanation for that in a second. And then finally, for 1 qubit gates, we're going to talk about the Hadamard gate. And this is probably one of the more complicated 1-qubit gates, at least in terms of its matrix. You can see here it's all of its entries are filled with 1/√2, and then the final entry is just the negative version of it. In simpler terms, what this gate does is if we give it the 0 state, it will output a state that it'll output a superposition that has equal probability of being measured 0 or 1. And this is also true for the 1 state. So if we feed in either of these, it'll give us a superposition that the 0 and 1 state are of equal probability of being measured. But you can see here the only difference between feeding 0 and 1 is that the probability amplitude for the 1 state is negated here. But obviously, if we take the magnitude and we square them, it doesn't matter. Their probabilities are exactly the same. And obviously, you can feed in a superposition as well. It doesn't just have to be the definite states, but the superposition is the result is not as clean. Okay, so sort of a question you might ask is, what are these gates doing? Like, why? Especially like the Pauli-X gate's probably the most intuitive, but these other two are like, why? So for example, why did we only make the probability amplitude for the 1 state negative? And then like what's going on with the Hadamard matrix? Because that matrix was not exactly the most pleasant thing to look at. But what's actually happening here is when we apply these gates, they're performing linear transformations. I mean, it makes sense. We're applying a matrix. But you can think about, at least for these 3 gates, that all of these vector representations of the qubit are being reflected about some line on the unit circle. And so in a sense, every quantum gate is rotating that the vector of the qubit. It's making a rotation about the unit circle. So for example, if we look at the Pauli-X gate, it's actually reflecting all vectors on the line at 45 degrees, which is y equals x. And that makes sense. So if we have the 0 state and we reflect it about this line, it turns it to the 1 state and vice versa. So it'll just sort of keep going. If we give it something with equal probability, it will just stay the same because it's on the line. And then if we give it something like at perpendicular here, so that would be the x value, the 0 probability amplitude is negative, the y is positive, but they're the same value. So it just goes completely down here. And let me just check. Is it correct to say that these are just transformation matrices? Yeah, I would assume so. I believe so. So, all right, and then moving on. So the Pauli-Z Gate does the same thing, except now we're dealing with the line at 0 degrees, y equals 0. So because the 0 state, the definite 0 state, doesn't have a probability, its probability amplitude for the 1 state is 0. So it's not going to actually make a change. So you can see it'll just stay the same. However, if we're in the 1 state, it's just going to make it negative. So it'll go down here to negative 1 state. And then finally, the Hadamard does the exact same thing, except now it would be the 22.5 degree line. So what ends up happening here is if we start with the 0 state, it's going to reflect, it's going to come up about here at the 45 degree angle, which will be equal probability of measuring the 0 state or the 1 state. And then if we go to the 1 state, this one's kind of a little bit harder to visualize, but it reflects it down here. And once again, it sort of puts it in equal in probability. Because it's probability, what happens when the qubit is measured to have the unexpected result. I will get into sort of what happens when we actually measure qubits in a little bit. But I mean, the basic idea is that it will either go into the 0 or 1 state, and because it's probabilistic, we can't predict which one it's going to go into. That's actually part of the reason why quantum computers have this probabilistic nature that makes them slightly less reliable, but I'll get into how we can improve that so that at least we can manage the fact that we may not get the result when we measure that we want. So I'll get into that in a little bit. So we kind of just went over talking about single qubits, but obviously you can only do so much with one qubit. It's not particularly useful. So a system of qubits is probably what we want to do because it allows us to bring in more qubits, allows us to represent more states. And so one qubit, as I mentioned, is not particularly useful, so we're going to add more. But the issue, once we start to add more quantum particles, is that we run into an issue that's a quantum physics related issue that's called quantum entanglement. And I'll explain a little bit what that means. Another issue that we'll run into, but we'll fix really soon, is we need a way to represent a system of qubits using just one equation. So we have, as I mentioned, an equation that can represent a single qubit, but if we bring in, let's say, 2 qubits, for example, we need a way to combine their equations so that we can represent them as a system. And so the way that we're going to do that is using something called the tensor product. So given 2 independent non-entangled qubits, we can combine their qubit equations by taking their tensor product. And the tensor product can be applied in to more than just 2 qubit states. Like I think you can also apply it to like 3 qubits, 4 qubits, etc. But for simplicity's sake, I'm keeping it to just 2 individual qubits. And so this little symbol, the circle with the X, that's the sort of tensor product symbol. And the process for which we combine them is actually really similar to how you would do foiling, like with a quadratic equation. So you would take okay, you take the first ones, so you take these, and you can see here, so the results here, alpha 0 times beta 0, 0, 0. So we basically combine these 2 states. And what that's ultimately saying is, think about what happens with this. If we take the magnitude squared of the state, we get alpha 0 squared, beta 0 squared, which is the same as saying basically that the probability we measure the first qubit to be 0 and the second qubit to be 0 is the probability we measure the first qubit to be 0 times the probability we measure the second qubit 0. So it, from a probability standpoint, makes sense. So we could do the first ones, then we do this one and that one, so that results in this state. Then we do this one and this one, which represents this state. And then finally the outer ones, this one and this one, which represents this state here. So obviously now we're dealing with a system of 2 qubits for simplicity's sake. And now there's 4 states that we have to deal with: the 0, 0 state, the 0, 1 state, the 1, 0 state, and then finally the 1, 1 state. And obviously it makes sense that this 0, 0 is like first qubit 0, second qubit 0, first qubit 1, second qubit 0, etc. And to represent a 2 qubit state, it's very similar to how we represent a single qubit state. We have a probability amplitude for each possible state. And the probability amplitude can be in the complex realm. It can be a real number. It can be positive. It can be negative. And once again, just because of how probability works, if we take the magnitude squared of each of these probability amplitudes and we sum them all up, the result should be 1, because there's 4 possible states. If we take the probabilities of all of those possible states and add them together, they should equal 100%. They should be 1. So now that we kind of understand what a system of 2 qubits looks like, I want to kind of give the following example. So this looks like sort of a very interesting state here, because I just showed you that there's 4 possible states, but this equation is only saying in this case, there's 2. And it shows equal probability of the 0, 0 state, which means both qubits are 0, and the 1, 1 state, which means both qubits are 1. So what is this equation saying? Well, what it's saying is if we measure one of the qubits first, because we don't usually measure them both at the same time, but if we measure the first qubit, for example, and it went to the 0 state, then without even touching the other qubit, without even measuring it, we already know what state it's in, because there's only one state that the first qubit is 0 in, and that's 0, 0. So if we measure the first qubit to be in 0, then the second qubit sort of already has to be in the 0 state, just because of what this equation is telling us. And then this would be the same if we measured the first qubit to be 1. the other qubit would have to be 1. So it's a very sort of interesting phenomena that occurs there. So the first thing is, can we split this equation into 2 distinct qubits? And the answer to this one is no. You can, obviously, in certain situations, decompose a tensor product and restore the 2 qubits individually. However, the issue with this equation is that these qubits are not exactly independent of each other, that the measurement, so what I was just explaining, when we measure the first qubit, it affected the measurement of the second qubit. So they're not independent of each other. So we can't really describe them as 2 separate equations because they aren't separated in a physical sense. And so what we say is, because we cannot talk about these qubits, these 2 qubits individually, we consider them to be entangled. And this, by the way, this state up here is what's known as a Bell state, which is just sort of an entangled state with the 2 possible states having equal probability of being measured. So what exactly is quantum entanglement? What is this phenomena that I sort of just described with that state? So if 2 qubits are entangled, what this means is that when we measure the first qubit, it affects the outcome of measuring the second qubit. It's not, so in that situation, when we measured the first qubit to be 0, the other qubit had to be 0 just because of what that equation said. When 2 qubits are entangled, it's not always a guarantee that the other qubit will go to a definite state, but what will happen is its probability amplitudes will be affected based on how we measured the first qubit. So in general, measuring the first qubit affects the outcome of measuring the second qubit. But however, one thing to note is that when you measure an entangled pair of qubits, this will automatically destroy the entanglement. So the entanglement only exists when we have not measured the state. But like in the previous Bell state I showed, once we actually make a measurement, then it will collapse to either the 0, 0 state or the 1, 1 state, which in that case, we can now talk about the qubits separately. They're either both in 0 or they're both in 1. They're no longer entangled. And this is a real world phenomena that occurs in quantum physics. And what's so strange about this is that if you were to take these 2 quantum particles, these 2 qubits, and you were to put them on opposite ends of the universe, that's about, I think, the biggest thing we can think about right now. We would still see that if we measured the first qubit on the one side of the universe and it went to the 0 state, then instantaneously the qubit on the other side of the universe would also go to the 0 state. And we didn't touch it. They're not physically connected, yet somehow the second qubit, the second quantum particle, is aware instantaneously of us measuring the first qubit. Now that's already strange because this idea that somehow there's sort of this instant transmission of information doesn't make sense because, I mean, Einstein tells us you can't break the speed of light. And if you're on opposite ends of the universe and the transmission is basically instantaneous, that far exceeds the speed of light. And this was actually the reason why, many scientists sort of initially didn't like this idea, were not sure about it, but we've performed experiments and it is a real phenomenon that occurs. And we honestly, this is one of those things in science that we just don't have a good answer for. We don't know why it happens, but that doesn't mean we can't take advantage of it or we can't understand it to some level. So now that we've kind of gotten the tensor product and quantum entanglement out of the way, we can start talking about 2-qubit logic gates. So just like classical computing has 2-bit gates, such as the AND gate, XOR, OR gate, quantum computing also has 2-qubit gates. These qubits, however, these gates must take a system of 2 qubits because we have to assume the possibility that the input to this 2-qubit state could be entangled, which in that case, an entangled pair can only be represented as a state. They can't be represented as individual qubits. So just for safety purposes, we just have the quantum gate always take in a system of qubits rather than 2 individual qubits. And another thing is that 2-qubit gates, or any gates with more than 1 qubit, could have the ability to entangle qubits. So that's just something we have to be careful about. And similar to the 1-qubit gates, these gates, we use a matrix to represent them. However, they are a 4x4 matrix rather than a 2x2, because now we're going to represent, since we have 4 states now, we represent that using a vector of size 4. So really the one, just for time's sake, the one gate we're going to talk about here is called the controlled NOT gate, C-NOT gate. And I mean, you could also, I guess, call it a controlled Pauli-X gate, because that is sort of the NOT gate that it's talking about here. But as I mentioned before, it is basically a NOT gate, so we just call it controlled NOT, C-NOT. And how this gate works is that one qubit is designated to be the control bit, and the other qubit is passed into a Pauli-X gate. So what is the control bit's purpose? What the control bit does is it either enables or disables the NOT gate, the Pauli-X gate. So if the control bit is in the definite 1 state, then the Pauli-X gate will be applied to the other qubit. However, if the control bit is in the definite 0 state, then the Pauli-X gate is not applied to the second qubit. The second qubit is just unaffected. And that all seems fine and simple, but the issue is, well, what happens if the control bit is a superposition of the 0 and the 1 state? What happens then? So that's a very interesting question, and we'll go over it in a second. So let's first off, this is the representation of the gate. The solid filled in circle represents the control bit, and the larger hollow circle is the Pauli-X gate. So that's the qubit that the NOT gate's being applied to. And we can see here's the 4x4 matrix that represents this gate. You can see up in this corner, you can kind of see an identity matrix, and down in this corner, you can see the X gate. And we'll see in a second just how this works in practice. So you can see here, given a quantum state, 2-qubit system with the following probability amplitudes: phi 0, 0, 0, 1, 1, 0, 1, 1. So you can see here, this is the vector representation. And what we do is we plug it into this matrix, and the result, as you can see here, the first 2 don't get affected. 0, 0, 0, 1, those 2 don't even get changed. However, the last 2 flip. You can see that they flip positions. And so what's happening here is, if you think about it, if this gate assumes that the first bit is the control bit. So you can see here with these 2 probability amplitudes correspond to the first qubit being 0. And if that's the case, then nothing happens, because the control bit's 0, so we don't end up applying the Pauli-X gate. So we see here why we use the identity matrix, because we don't affect those 2 states, those 2 probability amplitudes. However, in this situation, we can see that well, the control bit's 1. So what ends up happening is, for the second qubit, we need to flip the probability amplitudes, and that's exactly what we do here. And so once again, applying a 2-qubit state, a 2-qubit gate is very, very similar to how we do a 1-qubit gate, and we can sort of see how the C-NOT gate works on this given state. So now let's sort of talk about entangling 2 qubits, because it turns out that we can manually entangle 2 qubits. It's not just something that happens in nature. We can do it manually. So let's consider, for example, this is the C-NOT gate. For the control bit, we are passing in a superposition of equal probability of being measured 0 and 1. Then we also have a definite 0 state as the bit that's going to be passed through the Pauli-X gate. So you'll notice, though, what's weird about this is that the control bit is not the definite 0. It's not the definite 1. It's a superposition of the 2. So that kind of, in a sense, should put in your head that what happens, whether or not the Pauli-X gate gets applied, it's probabilistic whether that happens. So in a sense, what ends up happening is by running these through this gate, you end up entangling their probabilities together, that they sort of become dependent on each other. And you can see that the output, which I'll show the math behind in a second, is that Bell state I showed earlier. that now we only have the 0, 0 or 1, 1 state. These are entangled qubits at this point. And so the math behind it, the first thing we do, that's our control bit here, and that's the bit we're applying. We take the tensor product. Now, this is pretty simple. Basically, this is almost just like multiplication because we only have this one state here where we just multiply this 0 state into the other state. And we can see here, this just results in this system here where we have equal probability of measuring 0, 0 or 1, 0. But you can see in both cases, the second qubit is 0. And so now what we do is we take this, we turn it into a vector here, and we apply it to this matrix. And as a result, once we apply it, you can see here that this probability amplitude will go here and the 0 goes up, and we result in this state here. And you can see that now they are in fact entangled. Now, similar to some other quantum gates, if we were just to apply the C0 gate again, it would actually perform the opposite effect. It would put these last two back in their original positions, and they would be unentangled. Okay, so I've sort of gone over a lot of sort of the basics of quantum computing, understanding qubits, but what's sort of the actual use cases? Like, what are we actually going to use this for? So quantum algorithms are what we're going to talk about now, and they are designed to take advantage of the power of quantum computing. And there are quite a few famous quantum algorithms, but I'm only going to be really discussing one for the sake of time. And so we will be discussing something called Grover's algorithm, which is a quantum search algorithm, but just a few others if you want to look up on your own time are Shor's algorithm, which I mentioned earlier. That is an algorithm for finding the prime factors of a really large number, which is what you need in order to break RSA encryption. And then finally, Simon's algorithm, which is if you take like a quantum computing class, you'll likely learn about Simon's algorithm. It's a problem that was sort of designed specifically to show that quantum computers could solve certain problems faster. So once again, we will be looking at sort of a simplified version of Grover's algorithm. It's the actual one is it has a little bit more going for it, but what I'm going to sort of describe is the general process for which the algorithm works. So first off, as I've mentioned before, probably at the beginning of this lecture, quantum search algorithm, Grover's algorithm is a quantum search algorithm that's used to speed up unorganized searches from order n to order root n. The basic idea is that we'll create, if we have, let's say, we're going to, later on I use the example of just 3 qubits, just for simplicity. If we have 3 qubits, we take those 3 qubits and we put them in an equal superposition of all states. So all states are equally likely to be measured when we measure this quantum system. What we do, though, is once we do that, we apply a step of the algorithm. And what this algorithm does is for the element, the sort of the quantum state that we want to measure, it will increase its probability amplitude while simultaneously decreasing the probability amplitude of all the other elements. Then after we repeat the process root n times, we will have a very high probability of measuring the element that we want in the superposition. So let's sort of first talk about, well, how do we actually create this superposition? So let's, for the sake of example, say that we have 3 qubits. So that's states from 0, 0, 0 to 1, 1, 1. So we will start in the state 0, 0, 0. And that actually getting sort of the definite 0 state with all 3 qubits is pretty easy, because all we need to do is we just need to measure each of the qubits, because they'll either be 0 or 1. However, if for some reason one of them goes to 1 instead of 0, all we need to do is apply the Pauli-X gate, the NOT gate, and just turn it to the 0 gate, just turn it to the 0 state. So it's really easy to get to this like sort of reset 0 state. Then what we do is we apply a Hadamard Tensor 3 gate. And what this means, in a sense, this notation just means we apply a Hadamard gate to each qubit. And the result is that all of these states are now equally likely to occur. So if we were to measure this quantum state as it is it's your best guess what state it's going to result in, because I mean, they're all equally likely to be measured. So it's not really, this state is not particularly useful at this point. So what Grover's algorithm does is it will first invert the amplitude of the item we're searching for. So this is kind of where the simplification comes in, because the question is, well, if we're looking for this 100, how does it know that we need to invert 100? Because we're searching for it. So it almost seems like it kind of knows what we're searching for already. And as I mentioned before, it's a bit of a simplification. The actual algorithm is a bit more complicated because obviously we're looking for something we don't know. But this is just sort of the general iterations that Grover's algorithm performs in order to make this this quantum superposition have a very high probability of measuring the state that we want it to. So you can see here that all this does is we invert the probability amplitude of the state we're looking for, which in this case I just said is 100. Then what we do is we find the average of all the amplitudes. So we can see here, because we negated one of them, it's going to bring the average down. So if we just took the average as was, like with this being a plus, the average would be 1/2√2. Like, so it wouldn't, it would just be exactly what all of them are. But by making that one negative, it puts the mean to be a little bit less than all the other probability amplitudes. And so then what we do, this step is probably the hardest to explain, but we will invert all of the amplitudes about the mean that we just found. So in this diagram that I tried to make as best as I could, all these red lines represent all the other states. So the 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. So the red ones are the states we don't care about. And at this moment, they're all 1/√2, 1/2√2, 1/2√2. This blue one is the probability amplitude of the element we're trying to measure. So it goes negative, as you can see here. This black line is the y equals 0. So anything under it's negative, anything above it's positive. But we can see that because we made it negative, the mean is sort of below, slightly below all these other probability amplitudes. So what we do, and I'm going to try to explain this the best way I can, is if you imagine we take everything right now that's above this line here, and we just sort of flip it over the mean, you can kind of see it will sort of destructively interfere a little bit here, and will overall decrease the probability amplitudes of all of these red ones. However, for the blue state, the state we're looking for, we rotated about the mean the other way. So if you imagine from the tip all the way down here, all the way up to where the mean is, so we take that line and we flip it above the mean. And so as a result, we get a resulting state that looks like this. So here's the mean from earlier. You can see that all these other probabilities have decreased, as I've shown here. They've sort of destructively interfered and have now decreased. However, the probability amplitude for the element we want has like shot up. It's a lot larger now. So now if we were, even after one iteration, if we were to measure this quantum superposition, we would have a very good chance of measuring the state that we want. And so since we have 8 elements in this case, we need about √8 iterations, which in this case, we're going to round down to 2 because we don't want to overdo Grover's algorithm. It turns out if you apply it too many times, you can actually end up having the opposite effect. You can actually end up decreasing the probability of measuring the state that you want. So at the start, we have our equal superposition of all of the states. And then after the first iteration, you can see here that the probability amplitudes for all the other states dropped to 1/4√2, which I believe then puts it at a 1/32nd probability of being measured. However, the state that we do want to measure is now 5/4√2, which is 25/32 probability. So that's a really good probability that we're going to measure it. But if we apply it one more time, we can see though that all the other probability amplitudes, they've gone negative. So they're now below the y equals 0 line. However, they're still smaller. So if we take, this is, I believe, 1 over 128 probability that we measure any of the other states. However, if we look at the state we actually want to measure, it's going to end up being 121 over 128 probability that we measure it. So that's nearly certain at that point that we'll measure. And this is also sort of the reason why when I mentioned quantum computing being probabilistic is an issue, when you perform a lot of a quantum algorithm or a quantum experiment, you will likely end up with a superposition like this, where the answer that you want will have like the highest probability, but it won't be a certainty that you'll measure it. So what you usually have to do is you usually want to repeat quantum experiments multiple times. You want to repeat them so that if you know the answer is supposed to have the highest probability, that highest probability will sort of reveal itself after performing an experiment so many times. Okay, so before I sort of end off this, I do want to mention a few useful resources for learning more about quantum computing. So the first one is Qiskit. QI-Skit, I don't know exactly how it's pronounced, but this is by IBM, and it's a really great resource for learning about quantum computing. They basically have a whole textbook about, it'll mention a lot of the things I've mentioned, but then go into more detail. There's also IBM's Quantum Experience, which allows you to actually create quantum circuits and run them on real quantum computers. And I highly recommend that. It's really cool. And then finally, this is just a Wikipedia article dealing with quantum logic gates, which is what I generally talked about. And one last thing that I want to mention is if you kind of want to get a better idea of just how quantum computing works, I highly recommend looking into these, because it's still, it's still an emerging field. Quantum computing is still very, complicated. People who are working on quantum computers are still, trying to figure out how to make them better. But yeah, it's a really fascinating field that I personally hope, like, when I get further in my career, I can at least interact with some quantum computers, because I just think they're incredibly fascinating. But, they're weird because, you also have to deal with, of course, quantum physics now. So it just makes things a lot stranger. So I think that's really all I've got. So let me see if there's any questions. Is it possible to simulate quantum computers with classical computers? Yeah, you actually can simulate classical. You can simulate it on a classical computer, but you won't get. It doesn't always. It won't give you the exact same speed benefits that like nature will give you if you actually use legitimate quantum particles. So that, for one, that's just something that you can do. In fact, I believe Google was working with a quantum computer that they had suggested like solved a problem that like no classical computer could do in like a couple 100 years. And then IBM basically went and took their supercomputer, which was a classical computer, and simulated a quantum computer on it. And they did it not as quickly as Google did, but like in like a couple days they got the result. So you can simulate a quantum computer, and yeah, for debug purposes, I mean, yeah, I'm sure you can. It is, you can simulate it. You won't get the exact same speed up benefits that you would if you actually used quantum particles. Are there any other questions? What classes did I take for my math minor? I actually took a upper level matrices course, because as it turns out, like when you're dealing with any sort of the more theoretical sides of computer science, like machine learning, AI, quantum computing, like you use linear algebra for that. I mean, so as much as whether you like linear algebra, whether you hate it, whether you can't stand the sight of a matrix, it's very important to a lot of the more theoretical, the more researched fields, I maybe should say, of quantum computing. So I recommend it. I think especially if you're going into more research oriented or sort of more complicated areas of computer science, I think having a good math background is really important. Any other questions? Okay, so before you guys leave, I do want to leave you off with something. So let me actually just stop the presentation real quick. So before I let you guys go, I do want to share with you something that I made a little bit ago. What it basically is I'll post the link in, let me see, all panelists and attendees. I'll post this link here. So this is a project that I had made a while ago. And if you follow the link, let me actually just share this for a second. So what this is it's just a really simple, I called it Qubit Playground, and this allows you to sort of mess around a little bit with quantum particles, just sort of like just a basic representation. So this is supposed to represent a qubit, represented sort of in that unit circle representation I talked about. So you can see this arrows pointing to the state. We have a single qubit that's in the 0 state. You can see if we apply like the X gate, for example, it negates it. It will just sort of flip the state. If we apply a Hadamard gate, it puts it in equal superposition. Don't know why it went into the complex range there, but you can see it puts it in equal probability. And if we were to measure it, like it has equal probability. So in that case, it went to the 1 state, but we could do it again. And that time, like it went to the 0 state. And then you can also use 2 qubits, for example. So this brings up now 2 qubits. So using that C0 example I put out, you can put these in equal superposition like this. So you have your control bit as equal superposition, your second qubit as the definite 0 state, and apply the C0 with the first qubit being control, and they become entangled in this Bell state. If we apply it again, it sort of unentangles them. So this is just something if you kind of want to play around with quantum particles, I made a little bit ago, and you can see there's more. There's a lot more quantum gates, and there's actually a link to a Wikipedia article here that just will explain what these gates actually do. So yeah, I mean, that's really all I've got here. So you guys are good to go. If you have any more questions, you can put them in the chat. But yeah, have a good day, guys. Thanks, guys.